Okay, so in this video we'll talk about a very simple quantum circuit that'll create a Bell state. Here's how the circuit works. It has it works on 2 qubits. Each of them is initially in the state 0. And then we perform a Hadamard gate on the first qubit. And then we do a C0 with the first qubit as a control bit and the second qubit as a target bit. Okay, so this is our quantum circuit. So let's analyze what the output looks like. So first, let's try to understand what the state is after this Hadamard. Well, so it's 1 over square root 2, 0 plus 1 over square root 2, 1 for the first qubit times 0 for the second qubit, which is 1 over square root 2, 0, 0, plus 1 over square root 2, 1, 0. It's still a product state of the 2 qubits. But now, what happens when we perform a C0? So what's this output look like? So what the C0 does to it is, well, here the control bit is 0, so it leaves the second qubit alone. So you get 1 over square root 2, 0, 0. Here the control qubit is 1, so the target now gets flipped. So you get plus 1 over square root 2, 1, 1. This is our Bell state, right? So, and here's a bit of notation for it. This is usually called the phi plus state, for reasons that will become clear in a couple of minutes. Okay, so we now have this simple quantum circuit with 2 gates, which creates the Bell state. Now you could ask, what happens if you change the input qubits? So what if the input qubits were 0 and 1? Okay, same circuit, but the input qubits were 0 and 1. Well, what happens after the first Hadamard? Well, you still get 1 over square root 2, 0, plus 1 over square root 2, 1. And now the second qubit is in the state 1. What's this? It's 1 over square root 2, 0, 1, plus 1 over square root 2, 1, 1. And now what does C0 do to it? Well, it flips only in this case, right? It flips the second qubit. So you get 1 over square root 2, 0, 1, plus 1 over square root 2, and now this becomes a 1, 0. This is still a kind of Bell state. It's still maximally entangled. It's and this state is called psi plus. Okay. Now we could again look and see what happens if the 2 input qubits were 1, 0. Well, let's work this through. After the Hadamard, what do you get? You get 1 over square root 2, 0, minus 1 over square root 2, 1. And then the second qubit is in the state 0. So what's this? It's 1 over square root 2, 0, 0, plus, sorry, it's minus 1 over square root 2, 1, 0. And then what the C0 does to this is it flips that qubit, so you get 1 over square root 2, 0, 0, minus 1 over square root 2, 1, 1. So it looks very much like this Bell state we are used to, except that the phase here is minus. So this state is called phi minus. It's also another kind of Bell state. And finally, if you work your way through the last possibility, both qubits are 1. Okay, after the Hadamard, we'd get 1 over square root 2, 0, 1, minus 1 over square root 2, 1, 1. And after the C0, we'll get 1 over square root 2, 0, 1, minus 1 over square root 2, 1, 0. And this state is called psi minus. This is the famous singlet state. Okay. This is the state that occurs most often in nature because, for example, if it's with spin, then the spin gets conserved because it's 0, 1, minus 1, 0. Okay, so now these 4 states are called the Bell basis states. They form an orthonormal basis for 4-dimensional complex vector space of 2 qubits. How do you see that they're orthonormal? Well, one way you can do it is by computing their inner products and checking that they are 0. Here's another way you can do it. What you could do is realize that the inputs we had, the 4 input states we had to create these 4 Bell states, they are the standard basis. They are orthonormal. They are the standard orthonormal basis for dimensional vector space. This transformation is a unitary transformation because these are unitary gates. And so, since unitary transformations preserve angles, it follows that the output must also be orthogonal. And so that's how we know that these are an orthonormal basis for the state.